Okay, let's unpack this. If data is really the new engine of industry, then visualization has to be the dashboard.
Oh, absolutely. It's the refinery, right? It turns this raw, just overwhelming data into something you can act on, like, immediately.
And that's exactly what we're doing today. We are diving headfirst into the core toolkit for anyone who's serious about data science, Python's visualization libraries.
That's right. And our mission here is to give you a critical shortcut. We're not just going to, read off code snippets. We're dissecting the foundational sort of symbiotic relationship between Pandas, the data powerhouse, and then the plotting engines, matplotlib and seaborn.
Yeah, and we've really looked at how these three integrate with a very specific focus. Time series data. Time series is just notoriously complex. It's not just numbers, it's numbers in order. So we want to make sure you know how to use these tools to plot everything from big long-term trends to, tiny minute-by-minute anomalies.
And the goal here, it really goes beyond just knowing how to write the code.
Yeah.
We want you to have that critical thinking to know why you're choosing a specific statistical graphic, whether it's for a trend, a relationship, or a distribution.
So you become a better visual storyteller, making the right choice every single time. All right, so let's ground ourselves. Why do we even have statistical graphics? I mean, no one can look at a 1,000-row table of numbers and see anything meaningful.
Exactly. You just can't. Visualization is basically data compression for your brain. We need tools that give us that instant path to exploration.
It's the language of data science, really.
It is. And in the Python world, visualization is built on this layered foundation. At the very bottom, you've got matplotlib. It's the foundational library. You can think of it as this comprehensive canvas for drawing pretty much anything you can imagine.
And then on top of that, we get to seaborn.
Exactly. Seaborn sits on top of matplotlib, but it fundamentally changes the approach. Matplotlib is what we call imperative. You tell it exactly how to draw every little thing, every axis, every title.
You're the artist, step by step.
Right. But seaborn is declarative. It's data set oriented. It handles all that statistical heavy lifting for you.
But the real power-up happens when we bring in Pandas, doesn't it? If matplotlib is the foundation and seaborn is the specialist, then Pandas is kind of the glue that connects them.
That's a perfect way to put it. It integrates so tightly that if you have a Pandas data frame, you can just call .plot directly on it.
Which is a game changer for speed.
It's a huge game changer. And it's important to realize when you call .plot, Pandas is secretly calling matplotlib functions for you in the background. I mean, you can specify X and Y values, sure, but a lot of the time it's smart enough to figure out some sensible defaults just based on your data frame.
I always found that so cool that Pandas isn't just for cleaning data. It's an active part of the visualization process. The examples we looked at use the airqualityno2.csv dataset, and it shows just how simple it is. You can get a view of your data with one line of code.
Right. But that simplicity, it does raise a question you hear a lot. If Pandas gives me these quick and easy plots, why do I need to bother learning seaborn? Is it just for, prettier colors?
That's a fair challenge. I think the answer really comes down to aggregation. Pandas is fantastic for simple plots of the raw data, but when you need a visual that has complex statistical meaning, like, say, automatically showing a confidence interval, that's where Pandas' simplicity kind of runs out of steam.
And that's the gap seaborn fills perfectly. Speaking of complexity, let's talk about time, because time series data is where Pandas really, really shines.
Oh, absolutely. Dates and times are just inherently messy to manage, but Pandas makes working with those date-time objects so much easier. And there was a huge takeaway from the examples with that longer data set, the airqualitynottolong.csv. A tiny technical detail that saves so much time.
Let me guess, the parse dates argument.
You got it. In pd.readycsv.
Yes. If you just list the column names that have your time info, Pandas reads them as proper datetime objects right away. If you skip that, you're going to spend the next hour fighting with date strings.
Been there, done that. It's a critical first step.
Yes.
So once the data is clean, we have to move from just raw measurements to actual insights, which means aggregation.
Right, and this is where the mighty groupie comes in. This is how you shift the story from what happened at 3 p.m. to what usually happens on a Tuesday.
That's such a key shift.
It is. A great example we saw was calculating the average NO concentration for each day of the week, for each location. Think about the insight there. You're not just getting one average, you're comparing how pollution changes by day across different cities.
And why is knowing that daily average so important?
Because it gives you a baseline. If you know the average for Paris on a Monday is, say, 45, and next Monday it jumps to 70, you instantly know something is off.
It's an anomaly.
It's an anomaly that needs investigating.
Yeah.
Without that weekly baseline, you're just staring at a big number with no context.
And that leads right into plotting those patterns. Once we have that daily cycle, we can ask an even more specific question. What does the typical NO pattern look like during the day?
And that means grouping by the hour of the day and averaging across all the stations. This gives you a really robust view of when pollution typically peaks, like during rush hour, and when it bottoms out overnight. This is absolutely critical for real-world environmental monitoring.
Okay, so we've aggregated, but our data is still in that, long and narrow format. It makes comparing stations a little tricky.
Right.
To really get the most out of it for visualization, we need to restructure the table. And this is that aha moment that comes from the pivot function.
Pivot is such a fundamental tool. It takes your long data and transforms it into a wide format. For time series, the goal is always the same. Make the date-time year index and turn each location into its own column.
And the index you get back isn't just any old index?
That is so vital to understand. The result is a special Pandas object called a date-time index. And that class is not just for looks. It contains a ton of time series optimizations built right in.
So what does that actually do for you? How does it help?
It enables super fast time-aware operations. Because the index understands time, you can slice your data with simple strings like 2023-05 without any complex filtering.
So it just knows.
It just knows. And it lets you extract things like the year or the day of the week directly from the index, which makes your next group be even easier.
Which makes something like time slicing incredibly precise. We saw that example of plotting the NO-Euro values just from the 20th of May to the end of the 21st. That level of control lets you zoom in on one single event that might have been lost in the noise of the whole data set.
And if slicing is about zooming in, then the other side of that coin is resampling, which is about changing the frequency zooming out.
Right. So if you have hourly data, but your boss only cares about the monthly report.
Exactly. You need to resample, filter out the noise, and focus on the big picture. The process we saw was aggregating those hourly values to find the monthly maximum value in each station.
A classic business case.
It is. You're asking, in which month did we hit our peak? Resampling lets you switch from looking at minute-to-minute changes to seasonal extremes with, like, a single function. It's the difference between diagnosing a server crash and tracking a yearly budget.
And Pandas makes that switch just effortless. All right, so we've got the data perfectly molded, indexed, sliced, everything, thanks to Pandas. But we still need that tool for the heavy statistical lifting, the semantic mapping, the aggregation. And that's where we really shift gears over to Seaborn.
Seaborn is the statistical visualization expert, absolutely. And its declarative nature is the key. You just state the relationship you want to see, say, correlation between two variables, colored by a third, and Seaborn handles all the underlying matplotlib code.
So it makes sure the scales, the colors, the legends, all of it is statistically sound.
Exactly. It removes all that manual effort of, say, drawing a confidence band around a trend line. You get to focus on interpreting the plot, not on drawing it.
Which is the whole point.
The whole point. And for anyone listening who wants to practice, Seaborn even gives you its own load dataset API. So you get instant access to clean, famous datasets like TIPS or IRIS to experiment with.
That's super useful. Okay, so this brings us to the most critical part, knowing which chart to pick. The examples broke the plots down into 3 clear purposes. Let's start with trends.
Trends are simple, right? It's change over time. When you need to show how something evolves, you use SNS.lineplot. It's designed specifically for tracking data chronologically, and it makes it really easy to compare multiple groups on the same timeline.
Okay, so that's trends. Next up, relationships. This is often the most complex category, I find, because you're looking for connections between variables.
It can be. For the most basic relationship, 2 continuous variables, the scatter plot is king. Seaborn gives you SNS.railplot and SNS.scatterplot. And the real power is you can bring in a third categorical variable just by using a color or size parameter. Instantly, you have a multivariate analysis.
But sometimes you don't just want a cloud of dots, right? You want to actually quantify if there's a linear relationship there.
Exactly. And that's when you upgrade to SNS.regplot. This is a classic example of Seaborn doing the work. It plots the scatter points, and it calculates and draws the best fit regression line, often with confidence intervals, all in one go.
And what if you have multiple groups? Like, say, sales data for different regions, and you want to see if the trend is linear for each one?
Then you jump to SNS.lmplot. That function is designed specifically to draw multiple regression lines for all your color-coded groups on one graph. You can instantly compare different linear models.
Very cool. And beyond continuous variables, relationships can also be about comparison, like market share between different products.
For that, you're looking at SNS.barplot, comparing quantities across distinct groups.
And what about just spotting patterns in like a huge table of numbers?
For that, SNS.heatmap is essential. When you have a big correlation matrix, trying to see high and low values is impossible with raw numbers. A heat map makes those patterns just leap off the page with color.
Okay, so that covers trends and relationships. The final category is distribution. This is all about understanding the nature of a single variable. What values are possible and how likely are they?
For raw counts, the classic tool is the histogram. You get that with SNS.histplot or the older SNS.distplot. It just gives you the number of observations that fall into different buckets.
But histograms can be kind of blocky. What if you want a smoother sort of estimated distribution?
Then you turn to SNS.kdplot, which stands for kernel density estimate. It gives you a smooth, inferred shape of your data's underlying distribution. And crucially, it works in 2D as well to show the joint likelihood of two variables occurring together.
And for the ultimate distribution tool, the one that kind of packages everything together.
That would be SNS.jointplot. Love the joint plot. It is a complete analysis package. It shows that 2D KDE plot in the center, showing the combined distribution, but then it uses the margins to show the individual 1D distributions for each variable separately. It's the most high-fidelity, single-glance distribution analysis you can get.
So what does this all mean if we tie it all together?
I mean, we've basically mapped out a full workflow. Pandas is your workhorse. It structures, it slices, it pivots and resamples your data. It gives you that foundational date-time index that makes time series work fast and efficient.
And you pair that with seaborn, the specialized statistical tool that handles all the declarative mapping and aggregation.
Exactly. By using that combination, you move way past basic spreadsheet plots. You start creating complex, insightful, publication-ready graphics, whether you need to confirm a linear relationship or analyze a subtle shift in a distribution.
That fluency lets you, the listener, apply critical thinking to your data exploration instantly. You stop focusing on writing clunky code and start focusing on the actual story the data is telling.
That's the goal.
And the knowledge we've talked about, specifically choosing the right plot, is so key because the Rhine chart can completely hide the truth in your data. So here's a final thought. When you're under pressure to deliver an insight, and you see two patterns at once, say a clear monthly trend and a really strange daily distribution, the crucial question is, which pattern drives the decision you need to make right now? Do you start with the line plot to set a long-term strategy, or do you immediately use a histogram to pinpoint and fix an urgent hourly performance bug? Think about prioritizing the truth that matters most.